not? Should we say we do and not?
I would do that. It would be easier for me, but I'm not going to because it would. No, it's because your grades would go down like 14%, and I'd feel so bad. Like you need those points, and so for you, I'm going to give that test on Friday. So exam 2.
Wait, you're saying we're dumb?
Yes. 223, I think.
So no.
223. No. And the topics are through internal loads and beams. Okay, so we've already, the stuff we wrote down last time, the stuff we're doing today, that's not on the test. Anybody have any homework questions or any questions related to the test? I'll answer as much as you want, and then I'll go on to where we ended Wednesday. Yeah, I think it's the next day of class that you turn them in. A week from Monday, right? Yeah. Any questions?
I want to make sure that, well, I had one
Mm-hmm.
section not on as current as stuff on that matrix there.
Okay.
Number 4,
Mm-hmm.
section C, it asks which one is, like, which way you can multiply it. And
Oh, but it's 2 by 3 and 3 by 2, so you can multiply them both. You just get different things. Okay, no, that's totally true. Now, someday maybe I'll change that. But it kind of is, but it wasn't meant to be. But if you have 5, 6, 7, 8, 1, 2, 3, 4, and 1, 0, 1, 4, 1, 4. So the only way you can multiply these is where the left matrix has the same number of columns that the right matrix has rows. So you could do this. So if this is matrix A and this is matrix B, you could do B times A, but not A times B.
I thought it was the other way. The number of rows is the same number of columns.
Yes. A times B. Sorry, okay, so yeah, 1, 4, 0, 1, 1, 4 can be multiplied by 5, 6, 7, 8, 1, 2, 3, 4. Yeah, I know. So you're always doing dot products between rows of the first one and columns of the second one, so those have to be the same length. God damn it. Yes, I erased AB and wrote AB again. Okay, I made that seem more complicated than it was.
Oh, because there was, I thought it was,
BA.
no, it's right now.
Now it's right.
It's right.
Okay, so
Don't read the top part.
So could you not include this on the
it's confusing because the number of columns of this one have to equal the number of rows of this one. But what that's saying is that you take the dot product between rows of this one and columns of this one.
okay, so on the left, the number of columns has to equal the number of rows on the right.
Yes. And this is the dot product you're taking.
I like to write out A is 2 by 4, B is 3 by 2, and then I have the inside one.
The inside ones, yep. And so if you you can think of the formula like this: if you're calculating a matrix C. The ijth element of C is equal to the sum of, so if we're doing, so B, I, K, A, K, J. That's how you'd write like a program that multiplies matrices. And then that K, this this sum goes from 1 to whatever the number is of that circled, the number of elements in the rows of 1 and the columns of 2. If I ask you a question like that, one thing you can do is just type them both into your calculator and then see which one it gives you an error for.
I don't know why people laugh.
Yeah, sure. It's better than nothing. Always right. Yeah, exactly. Any other questions? Okay. So we are talking about stresses in beams. And that's broken up into stresses due to tension compression, stresses due to bending moment, stresses due to shear force, and stresses due to torque. We're done with this one, and we're talking about bending moment. So back to stresses due to bending moment. And we're still talking about the area moment of inertia. And I gave the formulas for a circular cross-section and a rectangular cross-section. And now I want to do an example where we have a more complicated shape that's made out of these simple shapes. So as an example, let's say that we have an I-beam. This is going to be a good I-beam. Okay, so like if you're doing the internal loads calculation, you're looking at it from this side, but the cross section is this. Okay, so we're going to calculate the area moment of inertia for that cross section that looks like an eye, and the dimensions are half a meter this way, half a meter this way, and then all of the thicknesses are 1 centimeter. And the coordinate system, just sort of to get our bearings, we'd have the x-axis going this way, the y-axis this way, and the z-axis this way. And then on the cross-section, the x-axis would be coming out towards us, y-axis up, z-axis to the left. Okay, first, let's think of, so there's a certain amount of material in this beam that we can calculate because, well, if we know the length, I guess. But, you know, say if you have some set amount of length, and so you could take that material and have it in, you know, form it into a different cross-sectional shape and calculate the area moment of inertia of that. So what would I sub A be? The same amount of material had a circular cross-section. So that would be a cross-section. We'd be looking with the y-axis up and the z-axis to the left. And the radius of this circle would be 1 centimeter. Not exactly, but almost exactly. And I sub A for this, I r to the 4th over 4. And that comes out to be 8.41 times 10 to the minus 9th meters to the 4th. Okay, so what we're going to see is that the area moment of inertia for the I-beam with the same amount of material is a lot bigger than that. And that means that if you apply the same bending moment to the I-beam, it's going to bend a lot less than this, and the stresses are going to be a lot less. Okay, so I'm going to break this up into a rectangle like that, that, and that, and they all have the same areas. Call this 1, 2, 3. And the area moment of inertia is all defined in terms of distances from the neutral axis. So what we want is the neutral axis of this shape, okay? Not the individual rectangles, the overall shape. Well, there are two lines of symmetry. One down here, one there. And so the centroid of this shape has to be at the intersection of those two lines of symmetry. Okay, so the centroid is right here. And so the neutral axis is like this. And so what we have to do is calculate the area moment of inertia of this rectangle about its own neutral axis, and then use the parallel axis theorem to calculate it about the overall neutral axis. Then same thing with this one, and same thing with this one. Okay, so area moment of inertia for one about, what should I call that? So out the axis for its own neutral axis. So eventually we're going to come down to this one. This is equal to 1/12 times the width, which is 0.5, times the height cubed, which is 0.01, and so we get a value for that of 3.25 times 10 to the minus 4. Oh, no, not yet. What do we get? It's something tiny. -8. Okay, it's little. And that's meters to the fourth. But that's about its own neutral axis. So now to calculate the area moment of inertia of rectangle 1 about A, that's 4.17 times 10 to the minus 8, plus the area of the shape times the distance squared from this O to A. And if you add all that together, you get 3.25 times 10 to the minus 4th. Okay, so notice that if you first just looked at this, you'd sort of wonder, like, what's the point of having this rectangle oriented horizontally? Because you get so much more value out of having the height big and the width small, you know? But then you see that this really isn't the contribution, the important contribution to this big area moment of inertia. This part might as well be 0. It doesn't even show up in this, you know, it's like a bunch of decimal points down. What does show up is the parallel axis theorem part. And what this shape does to increase the parallel axis theorem part is it gets the centroid of that shape really far away from the neutral axis. So it takes all that material and moves it far away from the neutral axis. Okay, and then rectangle 2. So I2, the neutral axis of that middle rectangle is the same as the neutral axis for the whole shape. So there's no parallel axis theorem part for this.
So d squared is the distance between the axis and the center.
Yeah, d is the distance in this case between those two bluish dotted lines. Okay, so this is 1/12 times the thickness, 0.01, times the height, cubed, that's 0.5. And you get 1.04 times 10 to the minus 4 meters to the fourth. And then the last one, rectangle 3, ends up working the same as the first one. So the area moment of inertia of 3 about its own neutral axis is 1/12 times 0.5 times 0.01 cubed. Fourth. And then the parallel axis theorem part, the area moment of inertia about A, the overall neutral axis is 4.17 times 10 to the minus 8 plus the area times the distance squared. The area of the bottom one is the same as the area of the top one. The distance from the overall neutral axis to the neutral axis is the same, and so you end up getting the same thing. And that is 3.25 times 10 to the minus 4th meters to the 4th. And now you just add up all these pieces. So the overall area moment of inertia about the neutral axis is I1 about A plus I2 about A plus I3 about A, and that's 6.5, 7.54 times 10 to the minus 4 meters to the 4th. And so compared to the area moment of inertia of that beam just being a long like tube, a solid circular cross section, this is almost 100,000 times as resistant to bending. I guess more like, well, a little under 10,000, but a lot more. Than the circular cross section. So if all that material, instead of being made into a I-beam shape, was just made into a long circular cylinder, and you applied a bending moment to it, this circular cross section would bend a ton more, the stresses would be a lot higher, and it would break a lot sooner. Okay, so finally, we're done with the area moment of inertia, and so now the formula for the stress due to the bending moment so first let's figure out what's causing this stress to occur, because it seems a little weird at first, I think, the way this goes. But so say this is a side view of the beam. And remember I said that the neutral axis is really a surface. It's a line if you're looking at the cross section, and it's also a line if you're looking in the X, Y plane. So if you're looking from the side, that's the neutral axis. And let's think about the two cases of bending. And let's think about also, I'll give these different colors. So the top, let's say that's blue, and the bottom is orange. And you can bend this beam two ways. You can bend it like this. And if you're bending the beam like this, is that a positive bending moment or a negative bending moment? That's negative. You know how you, yeah, that's how you know. Yeah. Oh, yeah, really? That's funny. Great minds think alike. And so this is, Experience some engineer developing this. They're like, yeah, we're going to do it this way. I think the engineers doing it were like, what's that mouth doing? Why does it look so weird? I was told I could listen to my radio at a reasonable volume. Okay, so this is positive M. This is negative M. Okay, so what happens to the lengths of those three colored lines? If you bend it like this, think about if you're running a track race around this strip of bacon.
You might want to
do you want
to your butcher for bacon.
Yeah, I'd probably cut the outside piece off, but the inside piece is still good. So which lane do you want? You want the orange piece because it's the shortest. And what happens when you bend this shape is that the orange part, the inside of the curve, gets shorter. And so that part's in compression. The outer piece gets longer. And so that's in tension, it's being stretched. And the reason that that center piece, the neutral axis, is called the neutral axis is because that's the one line in this view that stays the same length when you bend it. Okay, so that one doesn't change length. So here the top is longer, the bottom is shorter. The red line is the same length. With a positive bending moment, the top is shorter. The bottom is longer. And the line, the neutral axis that was the same length when you bend it with a negative moment is the same length with a positive moment too. Yes? That's the one, yeah, so if we defined it in the cross section, and it's the horizontal line passing through the centroid of the cross section. And that is the line that stays the same. If you extend that through all the cross sections, you get a surface. And then that surface is what stays the same length when you bend it. Yes, that's right. Yeah, the neutral axis, the way I drew it when I defined it, is pointing out at us through each one of those cross sections. And the formula for the stress, so what element of the stress is, what we have is tension and compression, okay? Depending on which bending moment you're applying to it, that determines whether you're in tension or compression on the top or the bottom. And if you're in tension or compression, with this coordinate system, what element of the stress tensor is this affecting? Tension and compression along the x-axis. So it's the xx normal stress. And so the formula for this is sigma xx is equal to negative bending moment times y over I. Yeah, you can write IA. I just have it written as I, but yes, it's that area moment of inertia. Y is, it doesn't have to do with the bending, it just has to do with the geometry before the deformation, how far above the neutral axis you are. So if you're on the neutral axis, that Y is 0. And so you don't have any stress due to bending at the neutral axis because it stays the same length. If you're above the neutral axis, so let's think about this negative bending moment. If you go above, that gets longer, so it's in tension. So we would expect this XX normal stress to be positive because it's in tension. And the way it would work is you have a positive Y, a negative M, the double negative makes it positive, and it comes out. If you're along the orange line, Y is negative, and so you have a negative, that's negative, so the whole thing ends up being negative, and you get compression.
So Y in this case would be 0.26 because halfway, like if you're at the blue line, it would be 0.26.
0.26.
Because the middle section is 0.5.
Based on the I-beam.
Oh, based on the I-beam. Yeah, it would be right, yes. 0.2, yes. And so, just due to bending, the stress is always highest in compression on one side and tension on the other side. And the part of the beam where you're least concerned about bending causing a problem is near the neutral axis. Okay, let's do an example. So let's say we have this beam and the loads applied to it are 1,500 newtons of tension and then a bending moment of 200 Newton meters on the two sides. So those are couples. They don't contribute at all to the force. And let's say that the cross section is a square. And the length of the sides are 2 centimeters. Okay, and we want to calculate, let's do it right at the middle. And let's say, where is the greatest stress? And we'll just do an absolute value. Along the dotted line. Well, in general, at every location, you know, if you move this dotted line around, you get different values everywhere. You're going to get different values up and down. In this case, just because of the way the loading works, we'd see that, I mean, all the internal loads are the same everywhere, and so the stresses are going to be the same everywhere. So we don't even have to know the length of that beam or anything to calculate this. All right, so let's calculate the internal loads. So I'll make the cut. So we're missing all this. We have a force of 1,500 newtons, a couple of 200 Newton meters, and then the internal loads that we need to, in order to keep this in equilibrium, we're going to need a tension or compression here, so that's T, and we're going to need a bending moment here, M. And the torque and the shear force would end up being 0. I'm just going to leave them off. So Newton's second law says negative 1500, 0, plus T0 is equal to zeros. So T is 1500 newtons. So the internal tension at the right end of our cut is positive 1500. So it's in tension at that point. And then the moment equation, this is about the z-axis. We have a positive moment of 200, because that's counterclockwise. And then plus m. We would have minus Vx, but there's nothing like that happening here. And so we get that the bending moment is negative 200. Okay, so the total stress tensor is the stress tensor due to tension compression plus the stress tensor due to bending moment. The other two would come out to be 0, otherwise we'd have to include those in there. And so the stress tensor due to tension compression sigma xx is equal to the internal tension divided by the cross-sectional area. So that is positive 1500 divided by 0.02 times 0.02. That's the area of that surface. And what's that? 4 times 10 to the minus 4th. So 3.75 times 10 to the 6 pascals. And so the stress tensor due to tension is positive 3.75 times 10 to the 6, and then zeros everywhere else. This is pascals. And now we have to do the stress due to the bending moment. We have to calculate the area moment of inertia. So in this case, that's just 1/12 times 0.02. Think of that as like the width times 0.02 to the third. What do you get for that? Okay. And that's meters to the fourth. And now notice that no matter where we are in that cross section, so think about the cross section, up or down, we're going to be adding whatever we get for this stress tensor, whatever we get for this x normal stress, we're going to be adding to the x normal stress that we got for the tension compression, which was positive something. Positive 3.75 times 10 to the 6th. So for the bending moment, we're going to get a positive XX stress on one side and a negative XX stress on the other. This is going to make the absolute value of the stress bigger for one of those and smaller for the other ones. You see how it sort of skews, pushes the whole thing? So it's not, the total stress isn't going to be symmetric anymore about the neutral axis. So the point that we want to consider on here is the one that has the positive XX stress, because then it's going to get farther from zero instead of getting closer to zero. Okay, so think about this case. We have let's look at this picture. We have a negative bending moment. So what's going to get longer? Yep, the top's going to get longer, the bottom's going to get shorter. And so the positive XX stress is going to be along the top. Okay? Who's with me? Anyone? Yeah, sort of. So we want to consider points along the top. I guess let's calculate them both, and I'll just show you how it works. But okay, so along the top, at the top of the cross section, sigma XX is equal to negative, and what was the bending moment? 200, negative 200. Okay, so negative 200 times y. Y is positive if you're above the neutral axis. So this is going to be 0.01. It's 1 centimeter from the neutral axis to the top, divided by that area moment of inertia we just got, 1.3 repeating times 10 to the minus 8. And so what do you get for that? Times 10 to the 8th pascals. And so the stress tensor due to the bending moment is 1.54 times 10 to the 8th, zeros everywhere else. And so at the top of the cross section, the total stress tensor is the one for tension plus the one for bending moment. And you get, well, the one for tension ended up being pretty small. So we got like 1.54375 times 10 to the 8th. And then zeros everywhere else. And then if we do that at the bottom of the cross section, the XX stress due to bending is negative of negative 200. This is below the neutral axis, so y is negative 0.01 divided by 1.3 repeating times 10 to the minus 8. And you get negative 1.54 times 10 to the 8th. And so the total stress tensor we get from adding up the one for tension and the one for the bending moment. And that's negative 1.537 0.625. Don't think too much about the significant figures I'm using here. That makes no sense. But I'm just trying to show how the two add up, 0, 0. And so in this case, it's not a big difference, but because of the way those stress tensors add up, you're more concerned about a fracture starting at the top of the beam than you are at the bottom. And that brings up.
So because the absolute value is like slightly more,
Right.
that's why you're more worried about.
That's right. Yep. But I mean, it isn't always that slight a difference. It could be a huge difference, You can come out where this is some big stress like this, and the other one is at 0. And actually, there are engineering cases where you're concerned about a fracture at a certain location, and so you apply some known, some additional, like internal load to the beam, so that the place where you're most concerned about it breaking, you've released a bunch of that stress through this, superposition idea. Any other questions? Okay, that's it. Have a good weekend.